Hello, I am Deepoo Kumar. I'm currently working as an assistant professor at IIT Bombay. I would like to thank GTT for this opportunity to present our work at this user meeting on the topic of application of private database development feature in FactSage for modeling the liquid state solution. The content for the talk is as follows. I'll introduce the topic and the issue of calcium solubility. We are developing this private database in this context. So briefly, I'll describe how to develop this private database in FactSage and then compare sort of benchmarking that private database with FTMISC for this FECAL MGO system. And then I'll also compare the results from the Kinetic model developed using two different databases. To introduce the topic in larger context of steelmaking, the steelmaking has two parts, the primary steelmaking and the secondary steelmaking, and followed by typically the continuous casting. In the primary steelmaking, the conventional route is the blast furnace BOF route, and now it's becoming more popular to use this electric arc furnace route to utilize scrap. And then that steel essentially free of by removing all the carbon, etc., is sent for the secondary steel making for adjusting the composition and also producing clean steel that is free of inclusions and dissolved gases, etc. In the context of modeling work regarding the secondary steel making, in the past, the focus has been on the mixing, to study the mixing in the ladle, and also study the changes in composition of steel and slag. In particular, there has been a lot of work on desulfurization. However, in past decade or so, the focus has been shifted now to develop a comprehensive model that can determine changes in steel, slag, and inclusion during this secondary steel making. And in this context, FactSage is quite popular. There has been a lot of publications in the last 10 years or so on the development of such a kinetic model. The result from such a kinetic model developed by Mariel Van Inde and Professor Jung is shown here. So on the y-axis is essentially the composition, steel, slag, and here inclusions, and x-axis is time. So you can see that the model is fairly successful in predicting or calculating the changes in steel and slag compositions. In the steel composition, the calculations are done for predicting sulfur, silicon, manganese, and aluminum. In the slag composition, there's a lot of calcium oxide, alumina, silica, MgO, FeO, MnO, sulfur, etc. could be predicted from the model. On the inclusion side, the top line shows the total inclusion content in steel adds inclusion fraction or mass ppm with time, and it also shows the composition as expected. In the beginning it has alumina inclusion, and as time progresses you have a pickup of magnesium and calcium, and you can see that the transformation from alumina to spinel and calcium aluminate happening in the process. To develop further, to understand or utilize this kinetic model, there have been a lot of work on inclusion predictions as well. And in this particular context of calcium solubility in steel, I would like to discuss the result for reactions between steel and slag, that is aluminum steel, and calcium oxide, magnesium oxide saturated slag. The ternary diagram on the left shows the inclusion composition in terms of mole fraction of aluminum, calcium, and magnesium normalized to 1, and you can see this the reaction is between steel containing 0.1% aluminum and slag saturated in calcium oxide and magnesium oxide. And the experiment was done in an MGO crucible using an induction furnace. The size of the melt was 500 gram, and the 75 gram slag was added. So the predicted inclusions at different times are shown here. The samples were taken at 0, 15, 30, and 60 minutes, and the predicted inclusions are mostly along this aluminum magnesium binary with stray pickup of calcium. However, if you look at the model results, you can see that there is significant calcium pickup. So there is certainly the deviation between the predictions and the measurement here. One way around to resolve this issue, as suggested by Liu et al., is to ignore the calcium oxygen associate. As you know that in FTMISC database, steel is modeled using the oxidation is modeled using the associate solution model. So you have calcium oxygen associate, aluminum oxygen associate, and then magnesium oxygen associate, etc. So when this calcium oxygen associate was ignored, you can find there is a better agreement between model and experimental result. So the model is also now along this binary line, which is a good news. However, this ignoring this calcium oxygen associate does not explain calcium pickup observed in some other cases that is discussed on the next slide. So during my PhD at CMU, I and other colleagues did a lot of experiments to understand under what conditions we can have calcium pickup. Very often under normal steelmaking conditions, we did not see any calcium pickup. So we tried a lot of combination of slag composition, crucible material, etc. And only in two particular cases we found significant calcium pickup. One was when you have 2 weight % aluminum containing steel that is in contact with double saturated slag that I was discussing in the past in the previous slide. And then another case was addition of 1 weight % electronic grade silicon in aluminum steel in contact with again this double saturated slag. So you can see this 2 weight % aluminum containing steel, so significant calcium pickup. These are all measured inclusion composition at different times. The star is at 60 minutes. And triangle is at 30 minutes. So you can see 30 and 60 minute samples so significant calcium pickup. Similarly, in the case of 1 weight %, here should be also 1 weight % silicon, 0.3 weight % aluminum. You can see that you have a fairly good amount of calcium pickup and after 15 minutes or so. So these were the two cases where we certainly saw the calcium pickup in our inclusion. And if we ignore this calcium oxygen associate, it does not resolve the issue. So if we ignore this calcium oxygen associate, it does not predict any calcium pickup even in these cases. So there's something certainly more going on, and the work is going on to try to resolve this issue. And we have started with this approach of developing a private database in FactSage that can be used with all other databases to predict this inclusion composition with time and then compare with experimental result. So in the solution module, the database can be developed by considering all this sort of end member formations here, and taking elements and associates here, and taking their free energy, enthalpy, entropy, etc. How to develop the database? That is available in the as a presentation in FactSage. One can go through and understand this. So the one challenge that we had was to reproduce FTMISC. Since our focus is on calcium, we wanted our model or database to predict or have the similar behavior for FeALO and FeMgO system. So there was some trial and error to find this value of free energy for associate formation for ALO, AL2O, and MgO, so that it predicts or it gives the same result as FTMISC. And then the CaO excess free energy that is shown here is adjusted to find some reasonable value that can explain some experimental observations. This is an ongoing work, so I'm going to present some preliminary results from there. So you can see here the solid line present the results from FTMISC. This y-axis is log percentage of dissolved oxygen, and here it is dissolved aluminum. And of course, when we say dissolved oxygen or dissolved, it's total dissolved, that includes associates as well. So you can see that the private database is fairly successful. Is almost same as gives almost same result as the FTMISC for FeALO system, and the same can be seen for FeMgO system. So now we have confidence in developing this such a private database. And now we move to the calcium solubility part. So again, we are seeing the similar thing, percentage oxygen and versus calcium, and Of course, the FT-MISC present has highest calcium solubility, and also you can see the graph shifted towards right and top, right and up, because it's of associate formation. Now, if we reduce the amount of associate formation by changing this free energy, excess free energy sort of here, we can see that calcium solubility comes down, graph shifts a little bit leftward. And this is the case which is essentially without the calcium oxygen associate formation, and you can see that that has the lowest value. So here you have some associate, and here you have the large amount of associate formation. Please note that the y-axis here is logarithmic, and that is why this last graph is not linear. Otherwise, you would expect that to be linear. Now, since we were discussing about the effect of aluminum on calcium solubility, because the different observations are made for low and high aluminum content regarding calcium pickup in the steel. So the condition here is 500 gram of steel containing variable amount of aluminum, and that is equated with 75 gram of slag. So the slag composition 51% CaO, 39% alumina, and 10% MgO. So as expected, you can see that FT-MISC with associate calculates the largest amount of dissolved calcium. These are equivalent calculations. And then private is somewhat little bit higher than the situation without associate, which is shown in more detail in this graph. So you can see that so without associate we have this value, and private has this value. So typically at 2 weight percent, if you see without associate case will have somewhat around 0.3, and private database will be somewhere at 0.7 ppm of dissolved calcium. And the with standard database in FactSage is about 13 ppm or so. Okay, so now I would move to the kinetic model, where the one of the issue regarding calcium solubility is due to the measurement issue. Calcium solubility is too low as expected from the inclusion analysis, and which makes it very difficult to measure. And we believe that in the previous literature there could be some issue in measuring total versus dissolved calcium as well. However, measuring the inclusion composition is much easier, and nowadays with automated inclusion analysis type of system, we can quantify that as well, quantify in terms of area fraction, and that can all the way be quantified to how much calcium pickup has been. So this steel slag reactions are modeled using this effective equilibrium reaction zone model, which has been discussed in the literature in detail. So I'm not going through that. The reactions that are considered in this model is steel slag reactions, steel inclusion reactions, which was initially will be alumina, and then we expect calcium and magnesium pickup. And then inclusion flotation was also considered, and this was supposed to occur at the same rate as the rate of steel moving to the steel slag interface. So the mechanism of change in inclusion composition can be described as a two-step process. In the first step, there is a reduction of calcium oxide and magnesium oxide at the steel slag interface. So calcium oxide in the slag can react with aluminum to give dissolved calcium and alumina in the slag. And similarly, magnesium oxide will give dissolved magnesium. These reactions are driven by due to very large activity of calcium oxide and magnesium oxide in the slag. Now that you have dissolved calcium and magnesium in steel, that is transported to this steel inclusion interface, and then these reactions happen in backward there, because at that interface, the calcium oxide and magnesium oxide activity is essentially 0 in the beginning, and then increases as the reaction proceeds. So essentially, the overall reaction is between the slag and inclusion, but it is mediated by the steel, and that steel mass transfer rate, etc., will come into the picture. Okay, here are the results. Again, we are looking at the dissolved calcium and the total calcium. So on the right side is the results from the private database. On the left side is the result from the FT-MISC solution database. So you can see that there is about 40-50 times different dissolved calcium predicted by the private database compared to the FT-MISC. Similarly, if you look at the total calcium, also we have almost similar behavior. There is an increase and then it's followed by some decrease in total calcium. The decrease is could be primarily of a couple of reasons. One is the flotation of calcium containing inclusions will essentially decrease total calcium in steel. And also could be that magnesium at the later stage when you have spinel to MgO transformation, the dissolved calcium in steel may itself come down. On the right side, we see the inclusion composition in terms of, again, cation mole fraction. Of course, the top one is the predicted inclusion composition using FT-MISC solution. Of course, T equals 0, you have pure alumina, and then you can see that there is calcium pickup. And this is the private database where we see very minor amount of calcium pickup and that at much later stage. Now, if the aluminum concentration is increased from 0.18% to 2.8%, you can again see the similar trend. However, compared to the previous case, now the calcium content has increased by twice in amount, and using the private database, there has been slight increase in the case of this one as well, FT-MISC as well. And similar trend you can see in the case of total calcium as well. And now you can see in this case the kinetics of calcium and magnesium pickup is much faster. So this is the case of FT-MISC, again, inclusion composition compared to this. Now here we are tending more towards MgO, and here you can see I was saying that the kinetics is much faster because this is again with respect to time. This is time equals 0, and it suddenly picks up a lot of magnesium, and then suddenly again you have a lot of calcium. So you can see, so again even further amount of magnesium and some amount of calcium. So the kinetics is much faster with 2.8% aluminum as well. Okay. So you can see in both cases there is limited calcium pickup. However, you can see the amount, even if you look at the private database, the amount gets almost doubled. So there's certainly the effect of aluminum is there, and that gives us more calcium. So I would like to conclude this here. This is a developing work, and we hope to have better. We want to include silicon as well in this system, and hope to develop or find an associate free energy value that can explain these results more accurately. So in conclusion, an associate solution model is developed in FactSage, and this module is an excellent tool to test some of the experimental data as well. Kinetic changes in inclusions during steel making may be used to test and understand the behavior of liquid steel solution. Especially here we are discussing about the calcium and magnesium pickup in steel. And more experimental data are required to resolve this complex deoxidation system. And as I said, silicon will be incorporated in this model. So with that, I would like to conclude here. Thank you very much. Before that, to end with, let me acknowledge some communication with Professor Inho Zhang, which helped in this development of private database. And then funding sources for procuring this FactSage in our department. Thank you very much for your kind attention. Please feel free to contact me if you have any questions using this email ID. Thank you again.